Script. Hi everyone and welcome. Today we're diving into a fun Leetcode problem called Snakes and Ladders. It's a classic game, but with a few twists we need to figure out. Our goal is to break down this problem step by step, making it super clear and easy to understand. So let's get started. Script. Okay, so we're looking at snakes and ladders. The main goal is to find the fewest dice rolls to get from square one all the way to the last square on the board. We're given this board, which is like an bi-grid. The squares are numbered from 1 up to squared. But here's a little twist. They're numbered in a special way called style. Think of it like, you start at the bottom left, go right, then the row above goes left, then the row above that goes right, and so on, like an old-fashioned plow moving across a field. We always start on square one. For each turn we roll a standard 6-sided die, so we can move ahead 1 to 6 squares from where we are. If the square we land on, let's call it, has a snake or a ladder, we must take it. The board tells us where that snake or ladder leads. If it's just a normal square, well, we just stay on. The game ends when we hit that final square, which is times. Our job is to find the minimum number of rolls. If it's impossible, we return -1. Oh, and a key detail. If you land on a snake or ladder, and it takes you to another square that also has a snake or ladder, you don't take the second one. Just one special jump per dice roll. Script. Let's imagine a board, say a 6x6 board, so it has 36 squares. We're at square 1, say we roll a 3. We'd count 1, 2, 3, and land on square 4. Now, we check the board. Is there a snake or ladder at square 4? If square 4 has a ladder that says, go to square 14, then boom, we jump to square 14. That whole sequence counts as one roll. Next turn, we're at square 14. We roll again, maybe we roll a 5. We count 5 squares ahead, aiming for square 19. If square 19 is a normal, plain square, we just land there and stay. That's our second roll done. We keep doing this, always trying to find the path with the fewest rolls to get to the end, square 36. And remember, that Boustrophedon numbering means square 2 might be next to square 1, but square 7 might be above square 6, going the other way. Script. So how do we tackle this problem? We're looking for the minimum number of rolls. Whenever you hear or shortest path in a problem like this, especially when the of each step is the same, like one dice roll, a great tool to think about is breadth first search, or BFS. It's like exploring outwards, level by level. First, we check all the squares we can reach in one roll. Then, from those squares, we find all the new squares reachable in a total of 2 rolls, and so on. This process naturally finds the shortest path in terms of which, in our case, are the dice rolls. Script. With BFS, we'll use something called a queue. You can think of it as a waiting line. We'll put pairs of information into this queue, the square number we're currently on, and how many moves it took to get there. We also need to keep track of squares we've already visited and fully processed. This is super important to avoid going in circles or doing extra work. For example, if we've already found a way to reach square 10 in, say, 3 moves, we don't really care if we later find another way to reach square 10 that takes 5 moves, because we want the minimum. Script. Now, one of the tricky bits is that Boustrophedon numbering. The game board is given to us as a grid, with rows and columns. We might look up a value like board at row R, column C, but our BFS will mostly be thinking in terms of square numbers like 1, 2, 3, all the way up to squared. So we'll need a little helper function. This function's job will be to take a square number, say square 17, and figure out exactly which row and column that corresponds to on the grid. And it has to remember that the direction flips for each row. Script. Let's think conceptually about how this helper function, let's call it getCoordinates, would work. Imagine is the number of columns or rows, since it's an DAF board. If we have a square number, first it's often easier to work with 0 index numbers, so we might think of it as quote square number -1. To find the row, counting from the bottom up, we could divide this quote square number -1 by, let's call that the row from bottom. Then, to get the actual row index as programmers usually see it, from the top, starting at 0, we can subtract this row from bottom, from n-1. For the column, it's a bit more involved because of the alternating directions. The column position will depend on whether our row from bottom was an even-numbered row or an odd-numbered row. Even rows from the bottom might go left to right, and odd rows right to left. We can use the remainder of that division, square number -1 modulo, to figure out the column, adjusting for direction. A script. Alright, here's how we can put this all together in Python code. It might look like a chunk of code at first glance, maybe a bit intimidating. No worries at all. We're going to break down the important parts, one by one, nice and easy, explaining what each bit does in plain English. The main idea is this breadth-first search strategy we've been talking about. Script. Okay, first up, we get which is the size of our board, how many rows or columns it has. Then, you see that getCoordinates function defined. That's our helper we just talked about, the one that converts a square number into its row and column, handling that tricky Boustrophedon style. After that, we set up our queue using collections.dequay, which is just an efficient way to make a queue in Python. We put our starting position into it. We're at square number 1, and it's taken us 0 moves so far. And really important, we create a set and add square 1 to it. This set will remember all the squares we've already processed, so we don't waste time exploring them again, if we can reach them with fewer moves, or just to avoid getting stuck in loops. Script. Now for the main part of the BFS, the loop. This while queue means, as long as there's something in our waiting line, keep going. Inside the loop, we take out the next item from the front of the queue. Using this gives us the current square we're on, and the number of it took to get there. The very first thing we check is, have we reached the target? If our current square is equal to times, which is the number of the very last square on the board, then we're done. We found a path, and because BFS explores layer by layer, we know this is the shortest path in terms of moves, so we just return the count. Script. If we haven't reached the end yet, then from our current square, we need to simulate rolling a die. A standard die has faces 1 through 6, so we loop from 1 to 6. For each roll, we calculate a next square candidate. This is simply our current square, plus the value of the dice roll, which is in this loop. Of course, we can't roll off the end of the board, so if this next square candidate is greater than times the last square's number, we just out of this inner loop. There's no point checking higher dice rolls if even a smaller one takes us too far. Seal script. For each valid next square candidate that we could land on from the dice roll, we first use our getCoordinates helper function. We give it the next square candidate and the board size, and it tells us the row and column for that square on the actual game board. Then, we figure out our final destination for this turn. Initially, we assume it's just the next square candidate we rolled to, but then we check the board. We look at the value on that row and column. If that value is not -1, it means there's a snake or a ladder there. In that case, our final destination becomes whatever number the board tells us to go to. If the board value is -1, it's a normal square, so our final destination just stays as the next square candidate. Script. Now, for this final destination, whether it was a direct landing from the dice roll or a jump from a snake or ladder, we check, is this final destination square in our set? If it's not in, it means we haven't processed this square yet, or at least not with this few moves. So two things happen. First, we add this final destination to our set, so we don't come back here again unnecessarily. Second, we add it to our queue for future processing. When we add it to the queue, we pair it with moves +1, because it took one more dice roll to reach this new state. If the main loop finishes, meaning the queue becomes empty, and we never return because we reach times, it means it's impossible to get to the last square. In that case, we return -1, just like the problem asks. Script. So how efficient is this BFS approach? Well, in the worst-case scenario, our BFS might need to visit every single square on the board once. Since the board is bi, there are squared total squares. For each square we visit, we do a relatively small, constant amount of work. We check up to 6 possible dice rolls, do a coordinate conversion, and a board lookup. So the time complexity is roughly big O of n squared. That means the time it takes grows proportionally to the total number of squares on the board. What about the memory, or space complexity? Our set needs to store, at most, all the squares if we visit them all. Similarly, the queue could, in some situations, hold a significant fraction of the squares. So the space complexity is also big O of n squared. Script. So let's wrap it up. For this snakes and ladders problem, breadth-first search was our best friend. Why? Because we needed the shortest path in terms of the number of dice rolls, and BFS is perfect for that, when each step has the same, in this case, one roll. A really crucial part was figuring out how to deal with that Boustrophedon numbering. We handled that by creating a helper function to translate a simple square number into its actual row and column on the board. And don't forget that specific rule from the problem. You only take one snake or ladder per dice roll. Even if the square a ladder drops you on is the start of another ladder, you stop there for that turn. Our BFS handles this naturally because we only check for a snake/ladder once after the initial landing spot from the die roll. BFS finds the minimum rolls by exploring layer by layer, which is exactly what we needed. Your outro script.